Hello, everybody, and welcome to another edition of Science Abounds, Science at Home, where we will discover home lab magic. In this channel, I demonstrate scientific principles, reactions, and concepts through experiments that are performed here in my home lab. In today's video, we're going to explore ampholytes. What are ampholytes? Well, in simple terms, they are molecules of ions that can act as both acids and bases, meaning they can donate and accept protons, depending on the environment. Key characteristics of ampholytes is that they have a zwitterionic nature. Ampholytes often exist as zwitterides, which means they can carry both a positive and negative charge, but the overall molecule is neutral. This occurs because the acidic group can donate a proton, while the basic group can accept a proton. Also, the isoelectric point. Ampholytes have an isoelectric point, or Pi, which is the pH at which they have no net charge. At a pH value below the Pi, the ampholyte will carry a positive charge, acting as a base. And at pH values above the Pi, it will carry a negative charge, acting as an acid. They also have buffering capacity. Due to their dual acidic and basic characteristics, ampholytes can also act as buffers in a given solution, helping maintain the pH within a certain range. In this lab, I'm going to demonstrate the amphoteric compound zinc hydroxide. It can react with acids and with bases. So depending on whether the solution is acidic or basic, the zinc flips behavior. All I need for this experiment is a solution, a 0.5 molar solution of zinc chloride, and then each 1 molar solutions of hydrochloric acid and sodium hydroxide. And I have 2 beakers to carry out the reaction. So let's get the demonstration started, and I will now demonstrate how ampholytes react. Okay, so we're going to start off with our zinc chloride in water solution. Zinc chloride dissociates completely. The zinc ion is a Lewis acid and exists as a hydrated complex in water. So I'm going to add about 100 mL of zinc chloride. And then I'm going to add about 50 mL of our 1 molar sodium hydroxide solution. And we're going to see what happens. So with the limited sodium hydroxide, I get a precipitation. Hydroxide ions react with zinc ions to form zinc hydroxide, which is a white gelatinous precipitate. This is the ampholyte in action. And as you can see, the gelatinous solution, it's a solid gelatinous precipitate. When you add an excess of hydrogen ions, which I'm going to do in a minute, but first I'm going to split the precipitate. Okay, so I just wanted to split that because one half I'm going to react with excess sodium hydroxide, and the other half I'm going to react with excess sodium hydroxide. So now I'm going to add an excess of sodium hydroxide. And what happens, the precipitate settles out, it crashes out and dissolves, and this precipitate dissolves to form a zincate complex. So that gelatinous precipitate of sodium hydroxide has now become a zincate complex. So in strongly basic solution, zinc is soluble again. This reversibility is a sign of amphoteric behavior. So now what happens when we add hydrochloric acid to that gelatinous precipitate? So that's what I'm going to do now is I'm going to add my hydrochloric acid, and let's watch what happens. The precipitate crashes out of solution. The acid neutralizes the hydrochloric acid if zinc is present as zinc coat. You can see the white precipitate with enough hydrochloric acid. So now you can see that zinc coat precipitate. But when we add enough hydrochloric acid, that precipitate, the zinc hydroxide, dissolves completely again with soluble zinc. So now we have soluble zinc again. Again, a demonstration of an amphoteric behavior and reaction. While that was a very simple but fundamentally important demonstration of an ampholyte. So what is the importance of ampholyte? Well, I've already mentioned that they have buffering capacity and help maintain pH balance. Ampholytes resist sudden changes in pH by accepting or releasing hydrogen ions. This helps keep biological fluids such as blood and intercellular fluids at a stable pH. They're also essential in protein structure. Amino acids, the building blocks of proteins, are ampholytes. Their ability to gain or lose protons influences protein folding, stability, and function. And along with maintaining pH balance, they support biological reactions. Many enzymes function only within a narrow pH range, and ampholytes keep or help maintain that proper pH needed for essential enzyme activity. Ampholytes are also important in industrial and pharmaceutical applications. They're used in the formulation of pharmaceuticals, cosmetics, and other biochemical products, and help stabilize solutions and improve product performance. Well, I hope you enjoyed today's video. Please hit the subscribe button. Also, hit the like and share button. It means a lot to me. It's very important in helping supporting my channel. Please leave me a comment. I love to hear your feedback. Feel free to email me. You can request a free copy of my video notes that I produce, giving all the important scientific information relating to the experiment in this video. Just send me an email. Until next time, keep on experimenting. Goodbye, everybody.